Welcome to our video about inverse trigonometric functions. So grab your unit circle and let's get started. First up, we have a warm-up. Go ahead and pause the video. Click play when you think you got it. The solution to the warm-up is theta equals 2 pi over 3 plus 2k pi and theta equals 4 pi over 3 plus 2k pi, where k is an integer, because we do have two angles on the unit circle where the cosine is -1/2. And of course, we wanted to also include all the infinite amount of coterminal angles to each one of these. In this video, we are going to talk about kind of what we just did. We sort of worked backwards and we were given a trig value. In this case, we were given the cosine of some particular angle and we needed to solve for that angle. We were going backwards. We were sort of inverting the idea of finding the cosine of 2 pi over 3 and getting out the answer of -1/2. Inverse trig functions are going to do this exact same thing, except we are going to have only one solution instead of a bunch of them on the unit circle. Here is that new idea. This is called arccosine. Now, arccosine simply means the inverse cosine and can also be written in a different way that looks just like this. We could also write this as cosine inverse of -1/2. These mean the same thing. Your book and most other math textbooks that I've seen lately use this form, arccosine, and so does the calculus book that you will be using next year. Therefore, I'm solely going to be using arc instead of the inverse symbol, but know that these two things mean the same thing. So what arccosine of -1/2 means is, give me the angle at which the cosine is -1/2. We know that on the unit circle there are two angles at which the cosine is -1/2. Our answer could be 2 pi over 3, and our answer could also be 4 pi over 3. Well, the idea is that we only want one answer. So what is it going to be? 2 pi over 3 or 4 pi over 3? We are going to be exploring the graphs of not only the cosine, sine, and tangent original functions, but also determine how to find their inverse, the arccosine, the arcsine, and the arctangent. Then we're going to see how this is actually a function and there's only going to be one particular output. Go ahead and take a guess at which one it'll be. We will return to this problem later. In the previous video, we looked at the graphs of cosine, sine, tangent, as well as all of their reciprocals. Let's take a look again at the graph of y equals the cosine of x. We can clearly see that this is a periodic function. It keeps repeating and repeating in the same way infinitely. We know that the cosine of 0 is 1, the cosine of pi over 2 is 0, the cosine of pi is -1, the cosine of 3 pi over 2 is 0, and then the cosine of 2 pi all the way back around is again 1. That is why this is called one period of the cosine graph or function from 0 to 2 pi. Well, if we were to just take that one period and we were to explore just that piece in here in between these yellow dotted lines, we can see that this is in fact a function. It does pass the vertical line test. Awesome. However, if we were to find the inverse cosine function, the arccosine function, would that be a function? Well, recall from earlier in the year, we learned about inverse functions, and a function has an inverse that is also a function if it passes not only the vertical line test, but the horizontal line test as well. So while clearly this snippet of the cosine curve is a function, is it a one-to-one function? Meaning, is its inverse also a function? No, that doesn't pass the horizontal line test here. I could draw horizontal lines in between here, and they hit the graph more than one time. So while this is a function, its inverse is not a function. It's not a one-to-one function. But we want to create an inverse cosine function. So it looks like we'll have to squeeze these two lines a little bit closer together so that we take only the snippet of the cosine graph that will pass the horizontal line test. Can you see where we'd have to move this yellow dotted line? We had to move it to pi. If we restrict the cosine graph only from 0 to pi, we can see that it's still a function, and it now is a 1-to-1 function from 0 to pi because it now passes the horizontal line test. Meaning if we were to create the inverse here from this little snippet of cosine, if we created the cosine inverse function from 0 to pi, it would also be a function. That is exactly what we're going to do. Recall that to create an inverse function, what we do is we take some xy coordinates on our original graph and then we swap them. So let's take 3 easy to see points on this green graph here of the original cosine function. This first one is 0, 1. This one right here is pi over 2, 0. And this last one down here is at pi, -1. So that means on the arc cosine function, which is its inverse, we will have the coordinate points 1, 0, 0, pi over 2, and -1 pi. Let's see what that looks like. Here is the graph of the arc cosine of x. We can see that it does not go on forever, neither does the original snippet of the cosine graph that we took the inverse of. Look, the point 0, 1 was on our original cosine function. That means the point 1, 0 is on our arc cosine or inverse cosine function. Then we had the coordinate point pi over 2, 0. 0, pi over 2 is on this graph. And then lastly, we had the point pi, -1 on our original cosine curve. That means -1, pi is on cosine inverse, aka arc cosine. So this is what the arc cosine looks like. Now let's take and compare the domain and the range. Of our original cosine curve, I'm only looking at the snippet in between here. So the domain goes from 0 to pi. And our range goes from -1 to +1. So those are the domain and the range of our restricted cosine curve. Let's take a look at the inverse cosine curve, or otherwise known as the arc cosine curve. We know that since these two functions are inverses of one another, that their domain and their ranges are swapped. That is something we have discussed earlier in the year. Let's see if that is in fact the case. So for our arc cosine, our domain should be what the range is for this one, from -1 to 1. And it is. Our domain, our x values, span from -1 to +1. So our domain here is in fact -1 to 1. And then our range should be what the domain of our original function was. So our range should actually be from 0 to pi. So our y values do in fact span down from 0 all the way up to when they equal pi. So our range is in fact from 0 to pi. I did a lot of explaining on this one just to get it set up. For the next two, we'll do a lot less explaining and just kind of go through the process a little more quickly for sine and tangent. Here is the sine curve. Again, it's periodic, it repeats. Let's take a look at one period. One period goes from 0 to 2 pi. The sine of 0 is 0. The sine of pi over 2 is 1. The sine of pi is 0. The sine of 3 pi over 2 is -1. And the sine of 2 pi back to 0. So this is one period. And remember, our goal is to get an inverse sine function or an arcsine function. Well, in order to create an inverse that is also a function, we do have to make sure that our original curve, our original function, passes the horizontal line test. Well, even just this one period of the sine curve does not pass the horizontal line test, because as we can see here, I'm already not passing it. Now this one's a little bit more tricky. We actually are going to move both of these dotted vertical lines in order to kind of get the best snapshot of sine. We do want to make sure that we're reaching the entire range from -1 to 1. So we're actually going to move this over here to -pi over 2, and then we want to move this one to where we will still pass the horizontal line test. So I'm looking here, I can't hit this. And then up here, I can't hit here. It looks like the closest I should go is right here at +pi over 2. That way, This snippet of the sine curve now passes the horizontal line test. It always passed the vertical line test. We know it's a function, but we want to ensure that its inverse is also a function. So we have now sort of sectioned off the part of the sine curve that we want, and it goes from negative pi over 2 to positive pi over 2. Here are 3 points that are on this section of the sine curve. Then we know if we swap those 3 points, we can create our arcsine function. Here it is, the inverse sine function, otherwise known as the arcsine function. Well, we can see that those 3 points are on our curve. So over here we had the point negative pi over 2 comma negative 1 on the original sine curve. So on its arcsine, its inverse sine, it should be swapped. The point negative 1 comma negative pi over 2 is in fact on here. 0, 0, if we take the inverse of that, it's still 0, 0. And then over here, we can clearly see we have the coordinate point 1 comma pi over 2. For our original sine curve on this restricted domain here between negative pi over 2 and pi over 2, the domain was, of course, negative pi over 2 to pi over 2. And the range, our output, our y values, span from negative 1 to 1. Then on our inverse sine, or arcsine, our domain and range should in fact be swapped, and they are. We can see that our domain here, from left to right, we span from negative 1 to positive 1, which was the range of our original function, and then the domain should be what then the range should be what our original domain was, and it does look like our y values go from negative pi over 2 to positive pi over 2. And there we have it. We have the graph of the arcsine as well as its domain and range. Tangent, the good old interesting one with the vertical asymptotes. Now, we could take a look at basically any period of the tangent curve, which is frankly just in between any two of these vertical asymptotes, so its period spans one whole pi. We're going to take a look at the one here that passes through 0, that goes from negative pi over 2 to positive pi over 2, open. Open in this case because we can't equal negative pi over 2 or positive pi over 2 because the tangent at those points is undefined. So what we are going to do is actually just use this in here, this one period here, find some points on it, and then create the arctan, or the inverse tangent function. Here are 3 points that are probably the easiest to find on the tangent curve in between negative pi over 2 and positive pi over 2. We have, of course, the origin, and then pi over 4, the tangent of pi over 4 is 1. And then note these go by 2's here to go up to 10, so this is where 1 is. And then this is the coordinate point negative pi over 4 comma negative 1. Here we have our arctan. It's kind of interesting. It's still just this weird squiggle. So again, we took the tangent function and we only took the section in between negative pi over 2 and pi over 2. So the way that we're writing that, the tangent function with a restricted domain, is a little bit different than how we wrote the restricted domains for sine and cosine, and that's because we are only having less than symbols here rather than less than or equal to. That is because our input for tangent cannot be equal to negative pi over 2 or pi over 2 as the tangent is undefined there. We have these vertical asymptotes there. So that's really that difference there. Then I do also want to point out that because we have vertical asymptotes at negative pi over 2 and pi over 2, with the inverse function arctan, those vertical asymptotes at those points turn into horizontal asymptotes at negative pi over 2 and pi over 2. And so those are just a couple other characteristics of a function and its inverse. Let's take a look at the domain and range. Our domain here on this with this restricted domain is exactly this right here. So our domain is open negative pi over 2 to pi over 2, open. Again, different from the sine and cosine where our domain values were closed. Then our range is actually all real numbers. The tangent function goes down to negative infinity on this side, and as we approach pi over 2 from the left, our function goes to positive infinity. So our range is actually all real numbers, which we can write in interval notation as such. Now, as we can see by now with this pattern, our domain and range for the arctan should just be swapped. So let's be sure that that is the case. Our domain should in fact be all reals. And as we can see, as we look from left to right, even though there's not arrows here, we are approaching actually the horizontal asymptotes on both the left and the right. And so we can see with the arctan, our left end behavior is negative pi over 2, and our right end behavior is pi over 2. We can plug in any value of x we want, and it will just keep going. So our domain is in fact all real numbers for arctan, and then our range for arctan should be between negative pi over 2 and positive pi over 2 non-inclusive. And if we look from down to up, we can see that that is the case based on these horizontal asymptotes here. We can never quite hit those two values, and they sort of bound our graph. So we just took a look at each one of these in depth, and this is like a nice little graphic that I found that sort of goes over all of it. So the first thing that we did is that we took a look at cosine and arccosine, its inverse. What you should have written down in your notes, if you don't have things graphed, that's totally fine, but what you definitely should have written down is the domain and the range. Now, I do want you to be aware that, of course, y equals the cosine x just in general has a domain of all real numbers. We can plug anything into it. This is the restricted domain that we're using that goes exactly with the inverse cosine. So the reason that we had to restrict the domain, as we saw, is so that we could have an inverse that was also a function. The range is, of course, from -1 to 1 with cosine, because we can never be smaller than -1 or larger than +1 as a cosine value on our unit circle. Then, of course, the arccosine, the domain and range are swapped. Then, moving on to sine, the next graph that we did, kind of the same ideas. Again, this is the restricted domain of this particular sine curve right here. And then the arcsine, of course, its domain is still -1 to 1, which is the range of the original sine curve. But the difference here is that its range is between negative pi over 2 and pi over 2 inclusive. The last thing that we looked at was the tangent curve. So be sure that you have the domain and range for both tan and arctan. Now, I do want to point out here that this definitely should not be closed parentheses here. I'm just noticing this. These should be open, as well as infinities should always be open too. So just my PSA, you can't trust everything that you find on the internet. Be sure that those are all open for tangent. All right, here's a really cool graphic that I like. I'm not going to explain this one super fully just yet. I do want to get into some examples, but this is a way to show the different ranges of the trig functions. We saw that the arccosine had a range from 0 to pi, and that's why this part's highlighted here, because on the unit circle, from 0 to pi means quadrants 1 and 2. Arccosine. We didn't talk about arccotangent and arcsecant, but it's good to know that those are there as well. Then, arcsine and arctan, we saw that their ranges, their output values, were between negative pi over 2, that's down here, and positive pi over 2, which is quadrants 1 and 4. Now, also arccosecant is there as well. So, what I recommend is sketching one. It doesn't have to look as intense as the one we just did. Is sketching one that looks more like this. And we'll see why in just a moment when answering questions. But it's good to see that for the cosine inverse, or arccosine, we're worried about quadrants 1 and 2. Whereas for arcsine and arctan, or sine and tan inverse, we are worried about quadrants 1 and 4. Now it is time to go back to that original problem from the very beginning. We wanted to know, what is the arccosine of -1/2? The arccosine of -1/2 is asking us, where is the cosine -1/2? Give me the angle at which the cosine is -1/2. All right, we already said that there were two spots on the unit circle where that's the case, 2 pi over 3 and 4 pi over 3. But as we know with functions, and hey, we just made sure that arccosine is definitely a function, we know that with functions, that with one input, there can be one and only output. We cannot answer with two answers. We can't say 2 pi over 3 and 4 pi over 3 because arccosine deserves better than that. Arccosine is a function. It needs one output. Which output is it going to be? Well, our output is our range. Let's take a look at this nifty thing that we just drew out, hopefully in our notes. For arccosine, our outputs, our ranges, our answers can only be in quadrants 1 and 2. So, which answer is it going to be? 2 pi over 3 or 4 pi over 3? It's got to be 2 pi over 3. And that is how we decide what the answer to arccosine of -1/2 is. It's 2 pi over 3. Because arccosine is a function, and for every input, it has to have exactly one output. The outputs are the ranges, and the ranges we found by doing the analysis of all those graphs earlier in this video. We came to this final conclusion. The outputs, aka the ranges, for arccosine, arccotangent, and arcsecant are only found in quadrants 1 and 2. That means you're only going to get one answer, ever. You should, they're functions. Then, for arcsine, arctan, and arccosecant, your outputs, the ranges of these three functions, are only found in quadrants 1 and 4. All right, finally, some examples. Number 1 looks a lot like the one we just did. We want the arccosine of 1/2. So where is the cosine 1/2? And we only need to look in quadrants 1 or 2. Well, I know that the cosine's positive only in quadrant 1 out of those two. So in quadrant 1, my cosine is 1/2 at pi over 3. So our answer, the answer to arccosine of 1/2 is pi over 3. Next up, we want to find the arcsine of root 2 over 2. Well, for arcsine, again, arcsine and sine inverse, those are the same thing. We are only looking in quadrants 1 or 4. So in quadrants 1 and 4, the positives would be in quadrant 1. So in quadrant 1, where is the sine root 2 over 2? At pi over 4. So the arcsine of root 2 over 2 is pi over 4. For number 3, the arccosine of negative root 2 over 2. For arccosine, we can only look in quadrants 1 and 2. That's where our outputs can be only. Well, I know cosine's negative in quadrant 2 out of those two, so in quadrant 2, where is the cosine negative root 2 over 2? That's a pi over 4 family. So my cosine's negative root 2 over 2 at 3 pi over 4. So our answer here is 3 pi over 4. Problem 4 is asking us for the arctangent of -1. Well, for arctan, or tan inverse, same thing, we only can have outputs in quadrants 1 and 4. I know that in quadrant 1 the tangent's positive, so I'm only looking in quadrant 4. Recall that tangent is y over x, or sine over cosine. Since tangent is y over x, and we want that y over x to be -1, we need our y and our x to just be opposites of each other, since when we divide y by x, and if they're opposites of each other, we'll get -1. It looks like that doesn't work here, but it does work here. X is root 2 over 2, and y is negative root 2 over 2. If we divide those by each other, we will get -1. Now, I cannot write that the answer here is 7 pi over 4, and here's why. If we take a look at the restrictions on our output here, our range, any answer that we write, it has to be in between negative pi over 2 and pi over 2. This is negative pi over 2, and this is pi over 2. 7 pi over 4 falls way outside of this interval. I have to call this something else. I have to call it a negative something. So I have to call 7 pi over 4 negative pi over 4. Because that falls into this interval here that we have to use for arctan, arcsine, and arccosecant when applicable. So basically, when you have outputs for arcsine, arctan, or arccosecant, and they're in the fourth quadrant, you have to rename them as a negative angle because of the restrictions on our output. So instead of writing 7 pi over 4, which technically is a coterminal angle to the correct angle, we need to write it as negative pi over 4. Remember, those are the same thing, because if we started at 0, which we always need to, and we go down pi over 4 radians, we're here. We're at 7 pi over 4. We've traveled 1 pi over 4 in the negative direction, and therefore this location here is also called negative pi over 4. And again, because of the way that the output is written here as this interval, we have to make sure it fits in that interval. These next two examples look a little bit more complex, but we will work through them from the inside out. So let's first take a look at number 5. We want the arc cosine of the cosine of pi over 6. It almost seems like arc cosine and cosine should just undo each other since they are inverse operations. Let's see if that's the case and if that's always the case. All right, the cosine of pi over 6, we know how to find this. We learned this a while ago at the start of trig. Pi over 6. Cosine is the x value. All right, the cosine of pi over 6, that's root 3 over 2. So I'm going to rewrite this as the arc cosine of root 3 over 2. Since the cosine of pi over 6 is root 3 over 2. All right, so next we are finding the arc cosine of root 3 over 2. Well, arc cosine, we can only get outputs in quadrants 1 and 2. Cosine is positive in quadrant 1 out of those two. So if we look in quadrant 1, where is the cosine root 3 over 2? It's like deja vu. I feel like I just did this. It's at pi over 6. So our answer is pi over 6. It does look like a function and its inverse kind of just undid each other, and we were left with kind of what we started with here. Let's see if that's the case also for number 6. We are asked to find the arc cosine of the cosine of 11 pi over 6. All right, let's start by finding the cosine of 11 pi over 6. 11 pi over 6 is down here, so the cosine is positive root 3 over 2. So we can rewrite this as the arc cosine of positive root 3 over 2. Okay, well, what is the arc cosine of positive root 3 over 2? Are we going to get back to 11 pi over 6? What do we think? Well, arc cosine has restrictions on it. The only outputs to any arc cosine can be angles in quadrants 1 and 2 only. So it doesn't look like we have a chance of getting 11 pi over 6 back since that's all the way in quadrant 4. We actually just solved this. We know what the arc cosine of 3 pi over 2 is. It's pi over 6. That's a little weird. Why does sometimes arc cosine and cosine sort of cancel each other out and we get out what we had put in, but other times that's not the case? Well, since arc cosine is restricted with its output to only quadrants 1 and 2, if we have a situation like this and this original angle is in quadrants 1 or 2, then we're good. But if we have a situation like this and the original input of the angle is in quadrants 3 or 4, it's not going to work. So we can't always assume that when we see an arc cosine and a cosine, or an arcsine and a sine, or an arctan and a tan, and so on, that they will just cancel each other out. I do highly recommend that you still go through the process because you might not always get what you put in. We got a couple more examples here. Number 7, we're starting with arcsecant. All right, so arcsecant is not something we've seen before, but we know how to deal with these inverse trig functions by now. So the arcsecant is right here, and we can only get angles out that are in quadrants 1 and 2 since we have restrictions on our range here. All right, let's figure out, first of all, where is the secant 2 in those top 2 quadrants? Well, in order for the secant to be 2, since secant is the reciprocal of cosine, we're really asked, when is the cosine 1/2? Okay, let's see when the cosine's 1/2. That is at pi over 3. So at pi over 3, our cosine's 1/2, meaning the secant is 2 here, since that's a reciprocal of 1/2. All right, that's in quadrant 1, so it looks like our answer is simply pi over 3. In number 8, we want the arcsecant of -2. All right, where is our secant -2 in these two quadrants once again, since those are the outputs that we can have? Well, secant is the reciprocal of cosine, and therefore it's negative in quadrant 2 out of these two. So in quadrant 2, we want to look and see again where is the cosine negative 1/2, since that would make the secant negative 2. It's reciprocal. It looks like that occurs at 2 pi over 3. So our answer here is going to be simply 2 pi over 3. Okay, we got a lot more going on with arcsecant here. In number 9, we have a more challenging problem. Let's work our way from the inside out and see what happens. We first want the secant of 5 pi over 4. All right, 5 pi over 4 is here. The cosine is negative root 2 over 2. So the secant is going to be the reciprocal of that. So let's first find out what the secant is going to be. It's going to be the reciprocal of negative root 2 over 2. So it's going to be negative 2 over root 2. Then when we rationalize, we'll multiply both top and bottom by root 2, getting us negative 2 root 2 over 2. So we're left with just negative root 2. Okay, so we replace the secant of 5 pi over 4 with what it equals. Again, secant's the reciprocal of cosine. Now we need to find the arcsecant of negative root 2. Well, for arcsecant, our outputs, our answers can only be in quadrants 1 and 2. Secant, I know, is negative in quadrant 2 out of those two choices. So in quadrant 2, where is the secant negative root 2? Well, I know it has to do with the pi over 4 family because I literally just did the reciprocal of negative root 2 over 2 and got negative root 2. So I know it has to be where the cosine is negative root 2 over 2 here. So the secant of 3 pi over 4 is in fact negative root 2. So the arcsecant of negative root 2 is where that occurs, which is at 3 pi over 4. So again, an interesting idea. We had an arcsecant and a secant, essentially inverse functions of one another, and when we plugged in 5 pi over 4, that's not what we got out. That's because 5 pi over 4 is down here in quadrant 3, which is not a part of the range of the arcsecant function. Number 10 is again dealing with arcsecant. We want to know the cotangent of the arcsecant of negative 2. So the first thing we're going to find out is the arcsecant of negative 2. We did this just earlier, and we want to know where is the secant negative 2 in quadrants 1 and 2. Well, I got to look in quadrant 2. Secant's the reciprocal of cosine. Therefore, the secant at 2 pi over 3 would be negative 2. So the arcsecant of negative 2 is 2 pi over 3. So we can replace that. So now this problem's asking us to find the cotangent of 2 pi over 3. Well, how do we find cotangent? To find cotangent, we take the cosine divided by the sine, or you can look at it as taking the x coordinate divided by the y coordinate at 2 pi over 3, which is what I will do. So at 2 pi over 3, our x coordinate is negative 1/2. And our y coordinate is positive root 3 over 2. The neat thing is that those 2's, because they're both in denominators of the complex fraction, can cancel out. So we are left with negative 1 over root 3. We do need to rationalize by multiplying both top and bottom by root 3. And so we will be left with negative root 3 over 3. To end the video, here are 4 awesome practice problems. Go ahead and pause the screen, take a few minutes to work on them, and hit play to check your answers when you're done. Here are the solutions to these 4 problems. If you got them correct, awesome. You are all done with the lesson today. Congrats. If not, stick around for the explanations for these 4. Number 1 is the arctan of root 3. So we are looking in quadrants 1 and 4 for where the tangent is positive root 3. Well, the tangent is positive root 3 when the sine is root 3 over 2, as we can see. So if we look here, again, the tangent's positive. out of quadrants 1 and 4, the tangent is positive only in 1. So we're looking here, it's clearly not the pi over 4 family. They don't even have a root 3. And it is pi over 3 because root 3 over 2 divided by 1 over 2, the 2's cancel, we just get a root 3. So our answer here is pi over 3. For number 2, we have the arc cosine of -1. Arc cosine means we're looking in quadrants 1 and 2. And also at these starting and ending points too. I mean, it's closed here for cosine. So where is the cosine -1 in these two quadrants and also on the axes here? The quadrant is negative, or the cosine is -1 at pi. In number 3, the first thing we needed to do was find the arcsine of -√3 over 2. So arcsine has outputs in quadrants 1 and 4. However, in this case, the sine value is negative of the angle we're looking to find. Therefore, we need to look down in quadrant 4. Now, when we're in quadrant 4, we do need to be aware of how we're writing our angles. They have to be written as negative angles instead of the angles that we literally see here. So where is the sine -√3 over 2 in quadrant 4? It's down here at 5 pi over 3. But because it's an arcsine function, we have to write it as an angle in between negative pi over 2 and positive pi over 2. So this angle of 5 pi over 3 is also written as negative pi over 3, since we've started at 0 and traveled 1 pi over 3 in the negative direction. So this is negative pi over 3. Then we are finding the tangent of negative pi over 3, which is right here. The tangent at this spot is the y value divided by the x value, which here we see is -√3. And lastly, in number 4, we are finding the arctan of the cotangent of negative pi over 4. So I could have written this actually as 7 pi over 4 in here because we're just taking the cotangent of something. I decided to write it as negative pi over 4 just so we get more practice with seeing angles like that. So negative pi over 4 is down here at 7 pi over 4. The cotangent there is -1, cosine divided by sine. Then we're finding the arctangent of -1. So where in quadrants 1 and 4, where our arctangent works, is the tangent -1. The tangent is -1 here at 7 pi over 4, again, needing to write it as an angle that fits in the interval between negative pi over 2 and pi over 2, so we cannot write it as 7 pi over 4, it needs to be written as negative pi over 4. Okay, I hope those explanations cleared up a little bit for you, and hopefully you understand the main idea behind inverse trigonometric functions.